Hi. So I'm going to talk about a new approach to verifying invariants of log-free data structures, motivated by a little consideration of the different trade-offs we can make in terms of how much effort we put into a verification versus how much benefit we get out. So if you think of it in these terms, we have a large body of work down here in the lower left, where with relatively modest effort we can get things like race freedom or deadlock freedom. And we have a large and growing body of very powerful work on concurrent program logics, where you can do a lot, but you have to pay a lot in terms of the effort you put in. But I'm really interested in this space here, because if you think about how people are going to get up there, there's stuff in between that they need to cover first. Things like external uniqueness, reference immutability, and refinement types are kind of in this intermediate space. And if we're ever going to get people up into that top right corner, they're going to actually work their way through some path of intermediate systems. So it's worth thinking about what are different points in this space, trading off effort versus verification power. So the particular space I'm interested in are techniques that describe or restrict mutation, usually with a type system, but do it in a way that's reusable, in the sense that you don't get one fixed property out. You don't just get data race freedom, for example. You got a small toolkit you can apply flexibly, usually for prohibiting certain problematic changes, rather than something that lets you recover Hoare triples. It doesn't necessarily guarantee that you've done the work you're intending to. And I'm particularly interested in this slice of the space, looking at reference immutability and refinement types, because it turns out there's slowly growing anecdotal evidence that these are things that actual developers are not immediately scared of. So that, in fact, there are actually people writing code now using reference immutability. So working in this space, this takes us to a new approach to invariance for log-free data structures, where we're going to cover both one and two state invariants of these structures. So when the data structure changes, we will have a say in how, not just what invariants are preserved. And this we're going to do in a way that also includes asymmetric protocols. So we can express symmetric things like monotonicity, as well as asymmetric things like producer-consumer relationships. We're going to do it in a way that gives us an intermediate verification burden. We're not getting Hoare triples, we're not getting contextual refinement. We shouldn't have to pay as much as you would for those richer properties. And we're going to do it in a way that's compatible with unverified but type-correct code. So what we're going to build on is some work from a couple years ago on rely guarantee references, which we're going to extend to work well for, be sound for concurrent programs, as well as extend them a little bit so they can actually reason about lock-free algorithms. We've implemented this twice, and I'll say a little bit about both. Once as an axiomatic Hawk DSL, as well as a library for liquid Haskell. So we'll get both some manual and automated forms of this. The underlying primitive that we're going to build on is called a rely guarantee reference, and it starts out as just a regular old ML reference that we're going to add a few pieces to give us more control over how it's used. So for starters, we'll add a refinement. I'm going to keep calling it a predicate because you'll see I use R for other things. But it's really a refinement type. It's a restriction on which of these T's do we actually care about, right? Maybe we only want positive numbers, for example. And then we have a relying guarantee, which have some similarities and some differences. Both are binary relations, and they constrain when the memory this reference points to changes, one of these relations is going to relate the old and new states. And the difference is which one matters, depending on who does the modification. The rely is going to be basically all of the aliases of some reference with this type. This is going to be an upper bound on the interference they can cause. This is a summary that we rely upon for local reasoning. And the guarantee is the reverse. It's a promise made to the rest of the program that this is as much as we'll use this particular reference for. Of course, for this style of reasoning to actually be sound, we need a couple more things that should be familiar to anyone who's seen rely guarantee-based reasoning for threads, like the fact that the predicate has to be stable with respect to interference, right? You can't say the value of this counter is always 5 if somebody's allowed to increment it. And the alias references have to be compatible in the sense that whatever one reference thinks it's allowed to do, whatever is in its guarantee, has to be contained in any of its aliases relies. All of its aliases have to expect at least that much interference. A little wrinkle that I'm going to gloss over for now and I'll come back to later is the fact that this predicate rely and guarantee in general actually range over both the immediate referent and the heap reachable starting from that heap cell. So if you have a pointer to the root of your data structure, you can talk about the whole data structure, which leads to a few complications that I'll come back to. Among them, the fact that this compatibility invariant is actually a bit more complicated. But for this talk, this is all the intuition you need. So for a concrete example, let's look at a monotonically increasing counter. So we'll start with two references, x and y, that point to the same shared counter. X, in this case, knows the lower bound on the value is 3. And its rely and guarantee in this case are the same. They both say the value will only go up. So when the counter changes, the old value will be less than or equal to the new value. Y is a little bit weaker. It has a weaker lower bound. It knows it's greater than or equal to 1. It expects at least as much interference as x can provide, so it knows some of its aliases might increment, but its guarantee is a little weaker. So y can only be used for reading, essentially. You could update the heap, but you'd have to restore the same value. So in this context, let's think about what it takes to type check an update through x and what its effects are on y. So if we're going to modify the heap at the location x points to, we need to prove that this is permitted by x's type, that we're respecting its guarantee, which means we need to prove that the value of x in the current heap is less than or equal to the right-hand side of the assignment, that value plus 1, which is straightforward to prove. And then because these aliases are compatible, this is expected by y. Y knows that this kind of interference can happen. And because y is restricted to only talking about things robust to its expected interference, we know that no matter what we try to do with x, if it type checks, it's not going to invalidate y. That's the main idea. And what I've described so far is basically prior work done in a sequential setting. But this is also well suited towards reasoning about fine-grained concurrency for a few reasons. Most obviously, we're already using rely guarantee reasoning in our specifications. And rely guarantee reasoning, in fact, originates in reasoning about concurrent programs. So we should still be able to use it for that. Second, if you look at a lot of lock-free data structures, many of them have natural 1 and 2 state invariants stated on a per node basis, which is exactly the granularity of specification rely guarantee references give you. And if you want a really nice exposition of this kind of idea, Peter Ernst's hindsight paper from a few years ago does this for a Heller set quite clearly. And the last main reason is that rely guarantee references play nice with unverified code in the following sense. They subsume regular ML references, right? If you're not actually constrained in any way by the rely, the guarantee, and the predicate, this is just a regular ML reference. So any code you could write in a more simply typed ML dialect fits immediately into this system. Which is important because often when people are adopting these kinds of techniques on an existing program, they want to start in one corner of their program. They want to start applying this in one part of their program without necessarily having to do some wholesale conversion effort. So essentially, unverified code, if it needs to handle one of these structures, can basically treat one of these non-trivial RGRefs as an opaque data type, basically a handle that it can pass off to operations that actually know what they're doing. So if we teach the previous system a few things about thread interleaving and about atomic memory accesses, then we can get code for things like an atomically incremented counter. So for example, we can read the value of the counter and try to compare and swap the value we read to that value plus 1. Since the CAS might modify the heap when it succeeds, we need to prove again that this, when it occurs, will respect the guarantee. We need to prove that this is something that's permitted by the monotonically increasing counter type. The form of this proof goal changes a little bit because we taught the type system a few things. But if you do substitution, you're proving x is less than or equal to x plus 1, which is still straightforward. Other structures, though, require a little more smarts. They require a little more sophistication. The main form that this takes is what we're calling refiners. So essentially, some proofs, some algorithms, what happens is you observe the heap at one point in time, then examine what you read out, which establishes some new property of the data structure you're looking at, which you then need to rely upon later on to discharge a verification obligation. So essentially, refiners are heap accesses that are going to relate the value you just read to a new stable refinement on the reference you read it out of. For example, if you think about a monotonically increasing counter, you might start out knowing that the lower bound is 0, the most general lower bound you can have. But if sometime later you compare the value in the heap to 3, maybe that's an important threshold for your program, you'd like to be able to strengthen that refinement and capture that knowledge back in the type of the reference. So we'd like to be able to move, in general, from a reference that says this is a non-zero positive number that will only ever increase to, after you read out something new into n, knowing that that's a new lower bound. So we can write that in our system as observe x as n, so you're naming the result, in a new stable predicate stated in terms of the value you just read out of the heap. And so type checking this requires us to, of course, prove this is also stable with respect to x's rely. And this leads pretty directly to a natural idiom of just accumulating invariants as you traverse the data structure. So you write the code you would, but every time you read an important piece of information that you'd like to remember later, you change the field read into one of these refiners. So this handles things like observing a new lower bound on a counter, looking at the final state of a protocol, which shows up in a header set, observing a fixed field value. So for example, in a Triber stack, if you want to prove that your pop pops exactly one node, you need to know that at the time of the cas, the next pointer in the node you're removing is actually the value you're going to install with the cas. Since you previously read that out of that same node, you can do it with a refiner, remember that value because the node is immutable, and exploit it later. And this scales all the way up to more complicated examples that actually we didn't even know about when we worked out the theory behind this, like a lock-free union find implementation. So Anderson and Wall wrote a nice paper in Stock 91, which no longer seems to publish concurrent data structure papers, for a lock-free union find implementation that includes the standard optimizations you would expect coming out of a data structures textbook. So it has rank-based union, it has path compression, and it preserves all the invariants that it needs to for that to work. We've given the first mechanized proof of invariants, both 1 and 2 state invariants for this structure. As an example, don't worry about reading it, but here's the code for find, for lookup. If it looks complicated, it's because the invariants for the structure are really complicated. If you erase all of the invariants in this and turn them back into regular field reads, you get exactly the code from the original paper. So algorithmically, there were no changes. And doing this, we actually came across some subtleties that were present in the original paper, but not actually remarked on in the original paper, which we found kind of surprising. Like the fact that the writes for path compression don't always actually compress the path. And in fact, there are executions in which temporarily the path will become longer because of one of these path compression writes. Because you might be in such a case, the actual data structure is an array of pointers to nodes, but conceptually, if you're about to reparent this last node to its grandparent to compress that path, before you complete your cas, all of your ancestors might get looked up and reparented all the way to the root, and now you're not actually compressing the path anymore. Right? Which is a little bit counterintuitive, although in hindsight, it makes, of course, perfect sense. A little side note, right now there's no actual verified proof of correctness for this. So if you're looking for a challenging example, this is also actually a weight-free algorithm. So another part of getting people to actually use something like this is automation. So the stuff I've described so far is heavily biased towards our Coq DSL, where all of the proof discharge is manual. And of course, we have a very expressive logic to appeal to kind of structure things as we might like. Now, automating that logic, as I've described it so far, is actually pretty hard. So I mentioned that because this predicate, the rely, and the guarantee reach over the entire heap reachable from that reference cell, this produces some tricky side conditions. So there are some side conditions in type validity and a few other rules that you need to think about and discharge. And these things they're annoying to think about, they're hard to think about, and they're also particularly hard to automate or infer, in part because these predicates over heaps never appear fully applied. There's no heaps in the program. So most existing inference tools don't handle that kind of predicate super well. So a slight simplification I'll propose is just throw away heaps. No more heaps in the specification logic, which at first blush probably sounds pretty extreme. And technically, yes, we are giving up a lot, but in practice, we don't actually give up a lot of useful expressivity this way. Because if we look at what we've done in the version of the system where we do have heaps, it's very rare that we go more than one link past the immediate referent. It's very rare that we go more than one extra step deep. So if we throw away heaps, we can actually give a fairly concise liquid Haskell library, where essentially what we did is basically wrap a bunch of existing IORef primitives with more sophisticated types that are aware of relies and guarantees. And if you do this, liquid Haskell has enough mechanisms that we can recover that one-step heap access pretty directly, in particular by exploiting support for indexing a data type by a predicate. Altogether, we've considered a few examples, a couple I've talked about in detail, and a few more. And the paper has much more detailed descriptions of all of these cases, including a very detailed description of the union find and its path compression challenges, as well as some discussion of idioms that show up in verifying rely guarantee references. So this accumulating path invariant is just one of them that we came across. Of course, we also have details on the formal type system. We have a soundness proof, as well as a qualitative comparison looking at the differences between developing with the Calc DSL or the automated form with liquid rely guarantee references, and also looking at proof burden. Since, again, coming back to the beginning, we're not doing Hoare triples, we're not doing contextual refinement, we shouldn't have such a high burden that if you were going to pay that, you could go do those things anyways. And if we compare on the same programs, our work to FCSL and very fast, we pay, it seems, roughly proportionally less proof effort and overhead. Thanks for listening, and also thanks to the Liquid Haskell folks for lots of bug fixes and support.
All right, we once again have plenty of time for questions.
Thanks for the talk. I wanted to ask about the code to proof proportion. How many lines of code do you have for each line of code?
Yeah, so sadly I neglected to put the table in a backup slide. But to a rough approximation, we pay, in terms of lines of code, which is, of course, a noisy number, somewhere between 1/6 and 1/3 of what you'd pay for stronger properties in systems like FCSL or very fast. For what it's worth, Ilya and I seem to have roughly similar taste in line breaks in Calc. But again, it's a rough subjective measurement.
Where does this fall down? Have you found examples of lock-free data structures where this is not enough?
It depends on which properties you care to state. So the main limitation of this technique is the fact that all of the specifications are attached to references. So if you don't have a reference between the parts of your structure, then you can't state the relationship. So one example is like an elimination backoff stack. The array you use for elimination doesn't have references to the actual stack itself, so it's difficult to express a relationship between them. You could imagine circumventing this by adding ghost state or a number of other things, but part of what we wanted to do was just stick to the simplest specification we could and see how far it got us, which we were pleasantly surprised. So I did look at that, and the short answer is I never finished. But I suspect that we can characterize in a general way the requirements for something to fit into the hindsight lemma or a generalization thereof.
Because you mentioned you can go with finite steps, but they have a pattern of errors.
Sorry?
So because you mentioned that you can go with finite steps, but they have
Yeah, cycles are one of the reasons these side conditions end up being pretty hairy sometimes, and it's one of the other reasons it's nice to get rid of them when we can. But in principle, actually, one of the, it's not in here, but in an AGDA prototype that I didn't talk about, I do have half of that paper implemented, and it looks like it works, basically. Of course, we need some theorems to back it up, but.
I have one last question on my part. So if you go to your list of data structures where you, I think it's maybe a multi-part question. So here, for example, with the Trieber stack, is it the fact that it's only there with Coq because you can't do it with the liquid Haskell restrictions, or is it just that it wasn't done?
I'm fairly confident that any of these structures, as we verified them in Coq, we could do in the liquid Haskell prototype.
Okay, so
it's a question of time.
What should I be looking for if I'm a programmer who's writing a lock-free data structure to figure out what I should do to make sure that I can stay in the nice liquid Haskell world instead of having to go do stuff in Coq?
In general, if you can state all of the invariants you care to prove in terms of just one extra hop as the reference, that's a good rule of thumb.
And it's one extra hop will pretty much always work with liquid Haskell. It's not some situation.
For the stuff we've tried with liquid Haskell encoding, which shifts a little bit from the observer formulation here. But that same power is there.
Any more questions? Okay, let's thank Colin again. And this was the last talk of this session, so let's also thank all of the speakers